Recording in progress.
Hey, hello. Oh yeah, it went well. I passed them. I was so stressed about it, but now it's over now, and it's like getting more calm, and until like 2 or 3 more weeks until like finals come up. Mhm. Thank you. Okay. Okay, so I could do Chem 8B first, do some problems with 8B, and then I could move on to 118A and then 118C. Kaylee, did you have any specific practice problems that you wanted to go over, or did you want to walk through the practice midterm?
I think like practice midterm.
Okay, practice midterm. Send a copy. Import. Key. Send a copy. And open. Okay, share screen. Okay. So let's work through these synthesis problems, because I think the synthesis problems are probably the hard ones, trying to figure out like what reagents are required to transform this reactant molecule into this product molecule, right? Where what is the functional group that you recognize in the reactant molecule here? What functional groups do you see present?
Wouldn't you have like your carbonyl and then next to like your OR group?
Yep. You do have a carbonyl and next to it an OR group, and that functional group is going to be called an ester. Right. What functional groups do you see present in the product molecule?
That'd be a carboxylic acid.
Yep. That would be a carboxylic acid where you have a carbonyl next to a hydroxy group. And we also have an alcohol, this OH group right here. So an ester is one of the carboxylic acid derivatives, where when we convert any derivative to a carboxylic acid, do you remember the reaction name of that whenever we convert a derivative back to the parent functional group, carboxylic acid?
Is it esterification?
Yeah, so esterification is going to create an ester. So if we have an ester and we try to create a different kind of ester, that would be a trans esterification. But whenever we go back to the parent functional group carboxylic acid, it's going to be hydrolysis. Right? Where we're making a cut between that carbonyl carbon and leaving group right there, and adding this group right there, replacing this leaving group. And the nucleophile what would be the nucleophile, do you think, that added that OH right there?
H2O.
H2O, yep, H2O. So H2O would be one of the reagents here, but H2O alone would not react with the ester because it's considered one of the less reactive derivatives. It's not the crazy two. It's not an isohalide or anhydride. So what does this ester need for the reaction to go through?
An acid catalyst,
Yep, acid
but
catalyst. Like
normally you can use H2SO4.
yep, acid catalyst like H2SO4. That's right. So these are the reagents required to convert this ester into this carboxylic acid, and this OH here is just the leaving group of whatever the ester was right there. Right. Okay. Okay. So now looking at the next one right here, we see that we have the same reactant as the last example, that ester, and now we have two alcohols. So we could say the first step was hydrolysis, giving you this product right here. And now we just have to think of a second step that would convert that molecule into this product here, right? Where the differences between those two molecules would be this carboxylic acid and this primary alcohol. Do you remember the reagent that would convert that carboxylic acid into a primary alcohol?
No, I don't remember that one.
Uh-huh. This one would be lithium aluminum hydride, a reducing agent. Lithium aluminum hydride, LiAlH4, and you could have a second step of H3O plus, right? Where this is talking about the reduction table where if we have an acyl halide, anhydride, aldehyde, ketone, carboxylic acid, ester, nitrile, or amide, or nitrile. For 8B, you learned about two reducing agents. The strong one, which is LiAlH4, lithium aluminum hydride, with second step H3O plus, or the weaker one, sodium borohydride, NaBH4, second step H3O plus. Okay. Okay. And if we were to react these derivatives with these reducing agents, we would get different products. Sodium borohydride, the weaker one, can only react with the first four. If we reduce the acyl halide, we would get primary alcohol, anhydride, primary alcohol, aldehyde, primary alcohol, ketone, secondary alcohol, right? No reaction for the lower reactive derivatives. But if we were to use a stronger reducing agent, lithium aluminum hydride, we can reduce all of these derivatives, even the weak, less reactive ones, right? But the ketone here would always, always, always be a secondary alcohol. Carboxylic acid, right? This is the reaction that the synthesis round tested for. Will react with the LiAlH4 to give this primary alcohol. Ester will also give us primary alcohol, but the amide would just give us an amine where we just get rid of that carbonyl right there. And the nitrile will give us this primary amine where this carbon of the nitrile right here is that carbon of the primary amine right there. Right. So that's that for this step right here. Now, in this question here, there's multiple correct answers here, right? Because we notice that there's an alcohol group and a lot of R groups right here, right? Where what you could have put here, there's a lot of things here. But when you see an alcohol, think of grignard reagents, right? In a lot of R groups, where the carbon directly attached to the alcohol would have been the electrophilic carbon, the dot carbon, right? And if that was your electrophilic carbon, the dot carbon, any of these carbons here could have been your starred carbon. So it doesn't matter which one it is. Which one do you want to be your starred carbon? The left, middle, or right?
The left one.
The left one? Okay. So if you want this left one to be your star carbon, this would have been your new bond that got formed between the star and dot, right?
Mhm.
Where the dot, the alcohol used to be carbonyl. So if we were to draw out what the reactant was before, that alcohol was that carbonyl right there, where this was the dot carbon right there, right? And that dot carbon was attached to a methyl group and whatever that R group is. This R group, which is that R group right here, and this methyl group, which is this methyl group right here, right? Making this new R group the group that attacked this dot carbon. So if we want that to be the star carbon, what does this carbon have to be attached to make that carbon partially negative, partial negative charge?
And GBR.
Yep, grignard reagent, MGBR. So we just copy and paste whatever that R group is, where that's the star carbon. And if we want that to be a star carbon, the negative charge carbon, that star carbon has to be attached to the MGBR like that. But that's the second step, because when we use this star carbon to attack that dot carbon, that would make that new bond between them. But when we push the double bond onto the oxygen, that oxygen will have a negative charge. What can we add as a second step to convert this O minus into the neutral OH?
H plus workup.
H plus workup, yep. Like H3O plus, or you could just put H plus workup. Did that make sense so far? Yep, that's good. Okay, now let's check his keys to see what he put as the answer. So the first step, he put basic conditions or acidic conditions. But in basic conditions, it would have been the deprotonated version. But for Helix's class, he says to assume acid workup. So you're safe using either route, right? But we did the acidic route, so that works. The next step here, he just put one reagent, lithium aluminum hydride, which works. It reduces this ester down into the primary alcohol and gets rid of that carbonyl, right? But the way that we did it is that we did the hydrolysis to get into this step, and then we reduced that carboxylic acid into the primary alcohol, which works. But we could have just done it in one step with lithium aluminum hydride, because when you think of lithium aluminum hydride, what is the atom you think of that has the negative charge?
Well, you think of the hydrogen having a negative charge.
Yep, the hydrogen with the negative charge, and this hydrogen with the negative charge is called the hydride ion, right? This hydride ion here is nucleophilic, which will attack that carbonyl carbon, push the double bond onto the oxygen, and get this intermediate right here. Hydrogen, which is this new hydrogen that we just added right there. Right. Now, the next step is, once we have this tetrahedral intermediate, you stop and you see if you have any good leaving group to kick out, which we do, this OR group. So we're gonna reform the carbonyl, break that bond, and kick out that leaving group to give us this intermediate right here, the aldehyde, the O minus, and we have excess amount of H minus. We technically have like a lot of them because it's LiAlH4. So we could bring in another H minus to attack this electrophilic carbon of the aldehyde and give us this negatively charged oxygen with those two hydrogens. And this oxygen is still negative charge, but the second step, H plus workup, would protonate the O minuses into neutral OHs, like that. Right? Any questions on this one?
Just so like what we wrote like before, and what Helix wrote, it's still like considered like right though, because there's multiple answers. Right?
Yeah, it's technically considered right. But his route right here is just that is shorter. What I did was I went to this route and then reduced it with lithium aluminum hydride, but it's still correct. It's still considered correct. Right. The next thing here, he made this carbon the dot, which it has to be the dot because that's a carbon, but he chose that carbon to be the star, the middle carbon, which is this carbon right there of the grignard reagent, like that, right? And there's other answers possible, right? Because you could have chose this to be the star or that to be the star, which is the same thing, and that's what we chose. Okay. Nice, nice. Okay. Any questions on this, Kaylee?
No.
Okay, that's good. That's good. Now let's move on to 118A. Wiley or Alicia, did you guys have any problems that you guys wanted to go over?
Um, I am a bit confused on like the SN1, SN2, or like E1 and E2. I kind of just don't understand the concept, or just like when we have to use them or when we don't. There was like, I mean, if we were to say specific problems, there's just like the lecture notes that Wei has, which
Yeah.
I uploaded. If that helps.
Yeah, so I could show you what I think about them and then give you a lot of practice, like problems based on what to choose between SN2, SN1, E2, or E1. The four factors to look for to differentiate, to choose between SN2, SN1, E1, and E2 is going to be the type of nucleophile and base. That's probably the most important one that I look at first. The other factor that you are going to look at is going to be your substrate, right? Whether it's methyl, primary unhindered, primary hindered, secondary, or tertiary. That's going to be your substrate. The other thing that we look for is if there's a good leaving group present or not, right? And the other thing that we look for is probably not that important, is if we are in a product or a product solvent. So that's the least important factor, right? You don't need to look at that factor to determine. You just need to have these three here: product or a product solvent, right? Okay, so I'm gonna show you the different types of nucleophiles and bases. You could either have a weak base, strong nucleophile. You could have a weak base, weak nucleophile. You could have a strong base, strong nucleophile. And there's two types of strong base, strong nucleophiles that you need to know. There's an unhindered type or a small base. And there's a hindered type or a bulky base. Right. So the easy list to remember is going to be the weak base, weak nucleophile. And the most common ones are going to be your neutral water and neutral alcohols, ROH, where R is any random hydrocarbon chain like ethyl, methyl, or isopropyl, right? And these are considered weak base, weak nucleophiles because they are neutral and they are very stable. And because they are stable, they are not reactive, making them weak base, weak nucleophile, right? Now, the next thing to look at is your strong base, strong nucleophiles. Whenever you have a negative charge on either an oxygen or nitrogen, automatically think of a strong base, strong nucleophile. Whenever you have a negative charge on an oxygen or nitrogen, right? And there's two hindered or bulky bases that you will see: tert butoxide, which is this tert butyl group with an O minus group. You might see it in the condensed formula like this with CONA or COK, and LDA. You might see LDA. Right. Those are the two bulky groups that you need to know. And the unhindered base are everything else, like hydroxide, ion, ethoxide, that nitrogen with a negative charge. It could be any RO minus, right? As long as the R is unhindered and not the tert-butyl. If the R is tert-butyl, then that would be considered a bulky base, right? So to make this unhindered, this is considered unhindered small. Even though it looks like long, it's considered unhindered because the carbon that is closest to the O minus only has one branch to it. But if we look at this carbon here directly attached to the O minus, it has three branches coming off of it, making that hindered, right? Now, everything else is going to be considered a weak base, strong nucleophile, like the Cn minus, N3 minus, the styles. You can see the halogens like Cl minus, Br minus, I minus. You might see phosphorus, but everything else would be considered weak base, strong nucleophile, right? Okay. And I'm going to show you what each type goes with what kind of reaction. A weak base, weak nucleophile tends to go with sn2 reaction. Weak base, weak nucleophile tends to go with sn1 E1 reaction. Strong base, strong nucleophile tends to go with E2 reactions. Right, sn1, E1, they go together. E2, there's two types of E2 you could have. If you use a small base, you're going to get the Zaitsev E2. If you use a bulky base, you're going to get the Hoffman E2. Right. Where
I think she gave us a little chart that that could help with that.
Yeah.
Here, let me just forward that. I kind of just screenshotted it just now, but it's on the left, the top left.
Top left. Okay, let's see. Let me see. Okay. Yeah. So that chart with those practice problems, let's go over that. So then I could teach you through the practice problems instead of me teaching like from the scratch. And then hopefully that would make it click more, right?
Okay, I hope that's better.
Yeah. Thank you. Let's see. Save. Share screen. Okay. Right here. I do also have a similar chart to that, which I could like import to this document. But let's see this chart first. Yep. Okay, yeah, this chart is going to be useful. I would put this in your note card for sure for this exam. Yeah, poor nucleophile. This is what I call weak base, weak nucleophile. Good nucleophile is what I call let's keep the same color. Yeah, color code, weak base, weak nucleophile. Good nucleophile is what I call weak base, strong nucleophile. Small base is what I call strong base, strong nucleophile, but there's two types, a small one and a bulky one. Right, but they're both strong base, strong nucleophile. Okay, yeah. So now, yeah, she also gave you like the list of nucleophiles here, where these are your weak base, strong nucleophiles. These are your weak base, weak nucleophiles. Wait, actually, I'll show you a different list because this one is like mixing a little bit of them. But to use this chart right here, right? Here's the step-by-step thought process on what I do. I first look at the type of substrate. Then I look at my type of nucleophile and base. And then I determine what reaction I have. Determine the reaction. And then you can use the chart, or if you understand it, which like will take a little bit longer time. But when you're first doing these problems here, you would have to rely on the chart a lot. Right. So if we look at the first example right here, this substrate here is primary because it's attached to one other carbon. We do have a good leaving group present, so that's good. This is a small, strong base, which is unhindered small, strong base. So when we look at the chart right here, this is considered a primary unbranched substrate. So let me show you the difference between a primary unbranched substrate versus a primary branched substrate. Right. Okay. So let's say we have this versus this, right? This is a primary carbon. This is also a primary carbon. But if you look at the carbon adjacent to it, that carbon is branched, right? Meaning that it has more than one branch attached to it. Another way you can think about it is that this is the substrate carbon, and this is going to be called the alpha carbon, the first carbon coming off of the substrate carbon. If the alpha carbon has 2+ branches, then it's going to be considered the substrate going to be considered a primary. I am mismatching this here. Now, unbranched, and this is branched. this is considered a branched primary substrate because this primary carbon here has a branch at the alpha carbon, right? Whereas this substrate here is considered unbranched because the alpha carbon has only one branch attached to it, right? So this is a primary unbranched substrate because if we look at the alpha carbon, that only has one like branch attached to it coming off of the substrate carbon. So when we look at the chart here, we have a small strong base, primary unbranched substrate. The reaction is telling us SN2, right? So let me show you the mechanisms of SN2, SN1, E1, E2, and then have you practice with those, and then I will move on to hydroversion oxidation, right? So for SN2, right, just doing the whole mechanism, I'm going to give you examples of each. Let's say we have this good leaving group, and I have this weak base strong nucleophile NaCN in a protosolvent DMSO. This is my substrate carbon right here, or the electrophilic carbon. This is my good leaving group present, so that's good. This substrate here is secondary because it is attached to two other carbons. This Cn minus here, right? Whenever you see sodium, always associate the sodium or potassium with a positive charge, and whatever is attached to the sodium or potassium is going to be negatively charged. So the negative charge here is going to be Cn. Right. This Cn minus here is going to attack the electrophilic carbon, kick out the leaving group, and it's going to invert stereochemistry, right? So when the Cn attaches, it's going to invert the wedge into a dash, right? Because this is coming from the backside. It's attacking from the backside by the backside attack mechanism, right? Backside attack, which inverts stereochemistry, right? So whatever the leaving group was, it will invert that stereochemistry. Because this leaving group was a wedge, the nitrile is now going to be a dash, like that. Right, so that's SN2. SN1, E1, they go together, and there's multiple steps. Right, and I'm going to show you two scenarios, one with, actually, let me show you three scenarios. One without a shift, the other one with a hydrogen shift, and the one with the alkyl shift. So let's say we have this oh, and another thing is that for SN2 reactions, right, I think yeah, it's all in the chart. So that's more of a conceptual thing, but you don't have to worry about that if you have this chart. SN2 reactions, they prefer to act with less substituted substrates like primary or secondary because of less stericogents. If this is a tertiary substrate, there would be like no reaction, or it would be an SN1 reaction because it would be too sterically hindered. But if we have as an SN1 or E1 reaction, we would prefer more substituted substrates like secondary or tertiary because of the carbocation intermediate. So I'll show you what I mean by that here. Okay. So if we react this substrate with a weak base, weak nucleophile like water, it's going to be an SN1 E1 reaction. And the first step of this mechanism is to kick off the leaving group, the good leaving group. Then we are going to have that carbocation intermediate, which is a secondary carbocation, right? And before we learn about the shifts, we have to learn about the carbocation stability. So the more substituted the carbocation is, the more stable it's going to be. Okay, so this is a tertiary carbocation, secondary carbocation, primary carbocation, methyl carbocation. And stability is going to increase from left to right because of something called hyperconjugation. Right. And the way that you can think about this is that the more groups or friends the positive charge has, the more stable it's going to be. That's because these groups here, they have a lot of electrons that are naturally or inductively going to donate electrons into the positive charge, making that positive charge stable. Right. There's less on the secondary and only one on the primary. The more R groups it has, the more stable it's going to be. So once we get to this tetrahedral mediate right here, we have to see the adjacent carbons and see if we could do any kind of shifts. So we see that it could do a shift on the left side because the left side is more substituted tertiary carbon. So we could move this hydrogen on that carbon, hydride shift, to have that tertiary carbocation right there. Right. And that makes this carbon here neutral now because this carbon gained a hydrogen bond, which is going to be that hydrogen that shifted with this bond right there. Whereas this carbon here lost the bond, it lost the bond to the hydrogen, making that a positive charge. Right. So now once that's good, I'm going to have the water attack the carbocation now, which is going to give us this new bond between the carbon and oxygen, right? Because this oxygen here is going to be the nucleophile. This carbon here is going to be the electrophile. This is the new bond between them. And the oxygen is now going to be positively charged because it has 3 bonds. Where the last step is to use another water molecule to deprotonate that positively charged oxygen and make it neutral. So that's the sn1 product, right? The E1 mechanism is the same thing. Kick out the leaving group, do the hydride shift. This is called a hydride shift. And then once we get to this more stable carbocation intermediate, this is going to be considered your carbocation, and these are going to be considered your alpha carbons, alpha carbon, alpha carbon, alpha carbon. Right. Draw out all of the alpha hydrogens, and then choose the most substituted one to make your most substituted alkene. Right. Because when we go into E1 and E2 reactions, it's going to be based on substitution. So that's an unsubstituted alkene, primary substituted alkene, or monosubstituted alkene. These are going to be your di-substituted ones, where geminal is going to be the same stability as cis, but trans is going to be the more stable. Tri-substituted, and then tetra-substituted is the most stable. Right. So the more substituted the alkene is, the more stable it's going to be. Right. Where this is unsubstituted, this is mono-substituted, only one R group. This is di-substituted, all of these 3, the geminal, cis, and trans. But the trans is more stable because it has less steric hydrogens. This is tri-substituted, and this is tetra-substituted. Right. One of these hydrogens here are equal. So, I mean, both of them are equal. So you could grab one of those hydrogens, make a double bond there, and get to your alkene product here. Right. Because when we grab this hydrogen right here, the bond between that hydrogen and alpha carbon is going to break and make a double bond right there, making this carbon now neutral because it gained a bond. It has 4 bonds now. So that would be your E1 product. But in most cases, the SN1 product is going to be major. E1 is going to be minor unless you add heat. Unless heat is added. Right. So yeah, SN2, SN1, E1, E2, like there's a lot that goes into it. I have to explain things in more conceptually, more detailed, because I'm skipping a lot of like small details here. But these are like the general concepts here. Where in SN1, E1, you have to look for any hydride shifts possible. If not, like let's say this is your most substituted carbocation, the water could just attack and give you SN1 product right there. And E2, that's the hardest one. E2 is the most complicated one. But I'll leave that for another office hours. So then I could like move on to 118, like the other question, and 118C and Johanna's question. But I hope that made more sense, Elysia.
Yes, it did. Thank you.
No problem. Okay. So the next question is going to be hydroboration oxidation. Right. This is going to be an alkene reaction where when we talk about alkene reactions, we could think about the regio selectivity of it, of the reaction. Selectivity. And we could talk about the stereoselectivity of this as well. Stereoselectivity. The regio selectivity of this reaction is going to be an anti-Markovnikov reaction. That means that the OH group is going to add on the less subside of the alkene, right? And in hydroboration oxidation, we do not have to worry about any shifts at all, right? There's no hydride shift, no hydride or alkyl shift, right? The stereoselectivity is going to be a syn addition with the hydrogen. So for example, if I were to give you this alkene right here, and I give you the hydroboration oxidation reagents, which is going to be BH3, H2O2, THF. Second step was like NaOH, water, something like that, I think. Let me double check the hydroboration. I know there's boron for sure and H2O2, but I don't exactly remember the order of this. Hydroboration, oxidation, reagents. Let's see. Yeah, so it says BH3 in the first step. The H2O2 is going to be on the bottom with the NaOH and water. Yeah, H2O2 is on the bottom and BH3 with THF on the top. Okay. Whenever you see these reagents, associate this with hydroboration oxidation, which would add alcohol on the less subside of the alkene. So this is our alkene right here. This is our more sub carbon. This is our less sub carbon. So what we're going to do is we're going to add an alcohol on the less sub carbon right there. Right. And this was a simple example because we didn't have any stereochemistry, but let's say we do have a chiral sensor. Like let's say we have so yeah, let's do that. Yeah. Okay. Yeah. So let's say we have something like this, and then react it with the hydroboration oxidation reagents. We have to analyze the alkene and see which alkene is the less subcarbon, which is this carbon right here. So we're gonna add an alcohol right there, right? But this is syn addition, meaning that the alcohol is gonna be on the same side as the hydrogen. So because that's a chiral sensor, I'm going to, let's say, make the alcohol a wedge. It could have been a dash as well because there's like a radical going on here in this mechanism. If this alcohol is a wedge, then that means the other side of the alkene, this side here, the hydrogen also has to be a wedge, right? Because this is syn addition, the same side. They attach on the same side. And if the hydrogen on this carbon is a wedge, that forces the methyl on that carbon to become a dash, like that, right? And you could put plus minus to show that you got the enantiomer version of that, or plus enantiomer, right? Because this could have been a dash, dash, and this could have been a wedge as well, right? So that's the basics of the hydroversion oxidation reaction. The mechanism is pretty wonky and weird because there's some migration steps going on, and that's what I would put on a note card and explain it. Right, the mechanism of that, I've barely seen it tested. Like it's like the course I've been teaching, 118B, hydroversion oxidation mechanism has never been tested. It's really wonky and weird. But I would still maybe put it in your note card just in case she puts it on the exam. But here's the important stuff that will show up on the exam: the regioselectivity of the reaction and the stereoselectivity of the reaction, and how to predict the product with this. Right. Did you have a chance of looking over the mechanism for this, Wiley? The hydroversion oxidation? Like there's like it's a really long mechanism. It's like 16 steps or something. Like with the 3 times thing, yeah, it's really weird. I know. It's super long. Yeah, I can like explain it to you, like hydroversion oxidation mechanism, but I'll need more time because like it's so detailed and confusing that it's like it can take like at least 15-20 minutes to explain the whole mechanism. Right, but here's what will be tested about this reaction. Right. Okay. Okay. Let's see. Hey Zinyan, do you have any questions for 118C so far? And then Johanna, I'll get to your questions after Zinyan's 118C question.
I think it's gonna be really long.
Mm-hmm.
I wanted to ask about like Claisen condensation.
Oh, Claisen condensation.
Yeah, in general.
Yeah, Claisen condensation. So, here's the general thing to it. The nucleophile is going to be an enolate ion, specifically the alpha carbon of the enolate ion. The electrophile is going to be an ester, right? And that ester has to have the OR leaving group attached to it. And the product is going to be a beta keto ester, right? And in this reaction, Claisen condensation requires or needs at least 2 alpha hydrogens. And there's 3 types of Claisen condensation reactions that you could have. You can have self-Claisen, you can have mixed Claisen, or you can have intramolecular Claisen. So I'm going to start with the most simple example, self-Claisen. Let's say we have this ester right here, and we react it with these reagents. The reagent has to be the same OR group as the ester. So if the OR group is this OR group right here, I want to use NaOR, where the R group is the same OR group as the OR right there. And I'm going to use the solvent, the neutral solvent right there. Right. So now, once we have this right here, whenever you see Na, that's a positive charge. Whenever you see whatever is attached to the Na is negative charge. So we have a negative charge OR right there, right? And that's our strong base right there, right? This strong base right here is gonna look for the most acidic hydrogen. The most acidic hydrogen is gonna be this alpha carbon right here, because when we deprotonate it, we're gonna have a negative charge on the alpha carbon, which is stabilized by this carbonyl, right? It gives us the most stable conjugate base. So we're gonna deprotonate that, make a double bond there, push the bonds to the oxygen, and that gives us our enolate ion. Right. But this O minus here is not our nucleophile. It's actually going to be this alpha carbon, because when we do resonance, right, when we push the bonds to the oxygen and give that carbon a negative charge, the negative charge on the carbon is less stable than the negative charge on the oxygen. And because it's less stable on the carbon, it's more reactive, right? So my star is that alpha carbon right there. So now I'm going to bring in another ester, because we have excess amount of that in the solution, to reform my carbonyl, have the star attack the dot, and push the double bond onto the oxygen like that. And that's going to make a new bond between the star and dot, which is going to look like this. So this is the most confusing part here, combining these two molecules. But I'm going to draw this part out first, which is going to be that carbonyl OR group. And this is going to be the star right here, which is attached to this methyl. But I drew that methyl group going down. In order for me to draw this new bond between the star and dot, and the dot is attached to ethyl group, O minus, and that OR group right there. Right. And now not the last step. The next step is to reform the carbonyl and kick out that bad leaving group. This is a bad leaving group right here. And when we do that, we are going to have this intermediate right here, where this bad leaving group here is very unstable. It's going to go back for its vengeance and deprotonate a second alpha hydrogen, create the enolate ion here, and that becomes this enolate ion. And we have our happy conjugate acid right there, right? And then you can have a second step of acid workup, H2O plus, to protonate the alpha carbon of the enolate ion, right? This O minus is not the base, because this enolate ion here, you have to look at it as a collective. This alpha carbon is more reactive because it's less stable when we do resonance. So that's the one that's going to get protonated when we reform the carbonyl. And our final product here is going to be this right here. And this is what we call a beta keto ester, because this is our carbonyl carbon. This is our alpha carbon, beta carbon, and at the beta carbon, we have a ketone. Beta to the ester, like that. Right. So here's like the general mechanism for Titan condensation.
I'm like getting confused. How is this different from aldol?
Yeah, so it's different from aldol because the electrophile for aldol would be an aldehyde or ketone.
Oh, okay. So it's just okay.
Yeah. And also
Like,
the
sorry.
product is different because the product for aldol would either be an aldol, like hydroxy beta to like a carbonyl, or an enone, alpha beta unsaturated carbonyl. But the product for Claisen condensation is a beta keto ester. So it's very similar. It's very similar.
So like the process is kind of the same.
Yeah, kind of the same, almost the same, except like the end part, because the end part here is we're not creating a double bond and kicking out an OH. We're just kicking out an OR group, and that OR group is going back for its vengeance to deprotonate another hydrogen. So it's very similar, but different. Different. It's different.
Okay.
Right. Yeah. Yeah, and in this one you can apply to like the mixed and intermolecular one as well. Okay. Yeah. Did that help, Xinyan?
Yeah, wait. So in intramolecular one,
Mhm.
you have like what would be like example of like the starting material?
Yeah, an example of starting material would be like if you had
Oh, yeah, just two ketones.
one
Oh,
ketone and one ester, because the electrophile
oh
has
yeah,
to
yeah,
be the
yeah.
ester right there. And your nucleophile would have to be this carbon, not this carbon, because that would make a 1, 2, 3, 4 membered ring. And that's unstable. We want to make a more stable ring, so that would be 1, 2, 3, 4, 5, 6. So the mechanism is still the same. Deprotonate the alpha hydrogen, make the enolate ion, and then go through with the reaction. But this time it's going to make a ring because it's intramolecular.
Okay.
Yeah. Right. Okay. That's good. Okay. Let's see. Hey, Johanna, did you have any questions for OChem 1 class?
Yeah, the worksheet I sent you,
Yep.
questions 14 and 13.
Okay, question 14 and 13. Let's do
Yeah,
that.
it was the one from yesterday.
Okay. 14 and 13.
Oh, and also with the question you told me to ask my professor, you are right. It was a typo
Mm-hmm.
on his
Oh,
part. Yeah.
dang. Did you ask your professor in office hours, or did you ask him during class?
It was just after class, like
After
we were
class.
able to, yeah.
Oh wow. Dang. What did your professor say? Like it was a typo, or like
Yeah,
did he
he said at first he was trying to justify it and then he realized the mistake and he was like, oh, it was actually a typo. And then, yeah.
Yeah, did you tell him like how it contradicted with the last example too? Like with
Yeah,
the thing? That's good.
yeah.
That's good. That's good. Yeah.
Thank you.
No problem. Let's see. Yeah. Okay, 13 and 14. Let's see.
Before anything, can I take a screenshot of?
Oh yeah. The mechanism.
Yeah.
Mm-hmm.
And also like the last page, the first page.
Right. Oh, the first one. This one.
Yeah.
Yep.
Got it. Thank you.
Yeah, no problem. Okay. What's right here? Okay. 13. Oh, didn't we do this one last?
Yeah.
Oh yeah, last night.
Yeah, that was
Oh right, that was the one. Okay. That's good. So you want it to do number 14 right here? 14? Okay. Below is an hnmr spectrum for one of the molecules in problem 11. Problem 11. What was problem 11? Okay, so it's one of those two. Determine which molecule and explain the relation of the hydrogens to the signals using all 4 pieces of information. So this is a zoomed in version of these 4 peaks right here, right? So I'm going to copy and paste the 2 molecules in problem 11 and then show you how to determine this. Right. So do you know the relationship between these two groups right here? Let's say this chlorine and chlorine, or in chlorine and NO2.
no.
Yeah, so they would be meta to each other. Do you know the position terms ortho, meta, para? Ortho,
Yeah.
meta, para? Right.
Sorry, I didn't know that's what you meant.
Right. It's okay. These two chlorines here are meta to each other because you can think of it as an M for meta, right? They make an M, or they are like 2 carbons away from each other, like that, meta. Right. And I think you watched my ortho meta para video. That's one unique hydrogen, that's another unique hydrogen, that's another unique hydrogen, and this is another unique hydrogen, right? Where as practice, what should be the multiplicity for this blue hydrogen right here? Like, should be a singlet, doublet, triplet, quartet, quintet?
Singlet, right?
Yep, singlet, because it has 0 neighbors. N+1, singlet. What about the pink hydrogen?
Doublet?
Yeah, doublet, because it has 1 neighbor. Nice. Purple hydrogen?
Doublet as well.
Yeah, so the purple hydrogen here will have 2 neighbors, the pink hydrogen and the green hydrogen as a neighbor.
Oh, yeah. So it'd be a triplet.
Yep, so it would be a triplet. Nice. The green one?
That'd be a doublet.
Doublet.
Only...
Only 1 neighbor. Correct. Right. So that is going to be the exact same as this other one right here. It's going to have the same splitting pattern, right? Because that is also meta. So this will also have a singlet, a doublet, a triplet, and a doublet. Right? Which we do see here. We do see a singlet. We do see doublets, 2 doublets, right? Which could be the pink and green ones. And we see a triplet, which is the purple one right here, right? S stands for singlet, D stands for doublet, and T stands for triplet, right? And these are the integrations right here. There's 1 H for each peak, and there's 4 peaks here, because we have 4 different unique hydrogens on the benzene. That's what the integration is, 1H, 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 like that. So the multiplicity here did not help us differentiate between this molecule and this molecule. What will help differentiate between this molecule and this molecule is how de-shielded the peaks are. Benzene hydrogens, they are usually between 6 to 8, right? Those are usually the benzene hydrogens. But notice how these peaks here are more de-shielded, more to the left side. It's like around like 7.5 to 8.5-ish.
Yeah.
Right? And if it's more de-shielded, that means that it is closer to or attached to stronger electron withdrawing groups. Because remember when I went over the hnmr with you, the more de-shielded the hydrogen is, the more it is closer to an electron withdrawing group that withdraws electrons from the hydrogen, making it de-shielded from electrons.
Yeah.
Yeah, right. Whereas if the hydrogen is bonded to a non-electronegative atom like carbon, it is considered shielded because carbon is not electronegative enough to withdraw those electrons from hydrogen, right? So now we have to compare the electron withdrawing group of chlorine versus NO2, right? We could ignore the other chlorine because they're the same thing. So chlorine is extremely electronegative. It's one of the halogens, so that withdraws the benzene ring inductively, right? It just naturally pulls the electrons from the ring because it has a high electronegativity. But if we were to look at NO2 right here, if I were to draw out the full structure of NO2, I would get this Lewis structure right here, with the nitrogen with a big positive charge, right? And because the very first atom attached to this ring, the nitrogen has a big positive charge, it's missing electrons. It's going to withdraw electrons from the benzene by resonance. So it's like it's actually taking the electrons actively, right? It's directly taking the benzene's electrons. It's directly withdrawing the benzene's electrons by resonance, right? This is electron withdrawing group by resonance. Whereas this is an electron withdrawing group by induction. The chlorine is an electron withdrawing group by induction. by electronegativity. It's not actually withdrawing by resonance. It can't directly pull out the benzene's electrons like this NO2 group is here. Right. So because the NO2 is a stronger electron-withdrawing group, the peaks would be more de-shielded this way. Right. So our molecule here would be this group with the NO2. Because the NO2 is a very strong electron-withdrawing group that de-shields the benzene peaks to the left. Right. If it was a chlorine, that we would expect it to be somewhere in the original region 6 to 8, like that. Right. But we see it a little bit more to the left side, a little bit more to the de-shielded side, meaning that we need a stronger electron withdrawing group, stronger group that withdraws or de-shields the hydrogens of the benzene, which is the NO2 here. Right. And I don't know if you went over like the electron withdrawing group power yet, because you were in OChem 1, and this is more of an OChem 2 reaction here. Have you gone over electron withdrawing group? Ortho para director versus meta director?
No, he did not go over it in class. He just showed us like how you said like ortho's like right next to it, meta's like at 1 and 2, like, but there was never a detailed. That's why I was searching for videos, because I was so confused.
Oh, and then that's where you found my YouTube video, and then
Yeah.
how did you find the school? Like, did you just check the description and then you like you just joined it?
I don't even know. I was just searching of anything desperate.
Oh shoot, I see. Oh my gosh. But did this help? Like, did that make sense?
Yes.
That's
And
good.
I also had a question, like with your video.
Mhm.
So you know how up top you said a singlet, a doublet, a triplet, and a doublet?
Yep.
So every time I see those peaks around an aromatic, is it safe to assume that it's in a meta position?
Yes. Whenever you see a singlet, a doublet, a triplet, and a doublet, it's safe to assume that it's a meta position. And another way that you can confirm that is that if you have 1H for each peak, right, that add up to 4 hydrogens.
Okay.
Because and a meta benzene ring will always have 4 different H's, and those 4 different H's will be represented by 4 different peaks with 1 H, like that.
All right.
Yeah, that's good. And then para is the easy one to remember. 2 doublets where each of these
Okay.
peaks will have 2 H's, like that. Right. That's good. That's good. Okay. Yep. So office hours are finished for tonight. Are you feeling much better for your exam tomorrow? I mean, on
Yeah.
Friday.
Yeah.
Tomorrow.
Tomorrow, my God.
I mean Friday. Friday.
You're good.
Not tomorrow. That's good. That's good.
Thanks so much.
No problem. Okay. Yes. So I'm going to end office hours here. And I'm gonna sleep early because I finished all my exams this week. So I'm just gonna sleep very well tonight. I was so stressed out this week and last week, studying, but I'm feeling much better now.
All right. Thank you. Bye.
No problem. See ya. Good night.
Thank you. Good night.
Bye. Good night.
Hello.
Hey Ryan. Hey. How's it going?
It's doing really good.
That's good. That's good.
Actually, you probably study about operons on biology or
Oh
something.
yeah, operons, lac operon.
Lac a Z, Y,
Yeah, Z.
lac Y, lac Z, trip.
Trip. Yeah. Oh my gosh. How's that going so far? Is it making sense?
Yeah, I've been using ChatGPT just to answer all my questions, just to like make it act like a teacher or something.
Right. And then you find it helping you, right? Like understanding the concept better.
Oh yeah.
That's good. That's good. I also use ChatGPT too to like help me with my assignments, homework, study tool.
Mhm.
Yeah.
Wait, let me find the. Because like you're already done with like stuff, and then you're just gonna take a big nap. So
I know. No, I'm just gonna sleep.
let's see, where is it? class notes. Is it this? Yeah, it was this one. Okay, let me share my screen. Overview of operons. All right. So, yeah, you know, like, okay, I'm gonna try to explain this, and then I'll just go to sleep, and then like I hit the save button on my head.
Yeah.
So this is operons are mostly only in prokaryotes and not in like eukaryotes, because eukaryotes have like a separate function for for transcription, and like translation is wait no operons operate in translation. Wait no wait. I'm looking over this. Like I'm just like trying to review right now.
That's good. That's good, because one of the best ways to learn or study is teach it to someone else, and also right before you go to sleep too, so then your brain processes what you just learned and studied. So that's good. Keep going. Keep going.
Yeah. Okay. So genes are made out of codons, and basically, tRNA carries an anticodon and a codon, and basically, what these tRNAs do is that they they don't transcribe anything. They bring the codons to wait, where's my other notes? Oh yeah, to the RNA polymers. And basically what they do is there's an A site, there's an E site, and then there's a P site. And basically the A site acts as like the key for RNA polymers. It tells us the RNA polymers to like, hey, get up. We're about to start replicating some DNA, or like some R. Wait, no, it's mRNA, because that's not double stranded. So yeah, and like basically they're just like trying to wait. Is it replication? No, it's they're trying to make proteins basically. Because yeah, right here, like the operon is operon is basically an off and on switch to the bacteria, like how they because like certain proteins like shouldn't are like are turned on, and like they like operons just like are turned on forever, and then um some operons are turned off until like they're needed, like trip, where like wait, what's the name? Tryptophan. Wait, let me wait. TRP, and then tryptophan. Okay. So things like lac, which is like is basically makes the protein for lactose, which makes basically is in milk, but not is wait, lactose. Okay. Lactase is the protein that breaks down the material for lactose, and that's what lac Y and lac Z do, but I don't know what both of them do. So I'm getting there. I have information. Are you there? Wait, hello?
Oh, hello. Yeah, I'm
Oh,
here.
okay, good.
Can you hear me? Can you hear me?
I can still hear you. It's like he stopped talking. Is he okay?
No,
It's
no,
like,
no. I'm just listening. Yeah, finishing up my dinner. Listening. You study, teach,
okay,
me.
yeah, just eat in and then like yeah.
Eat and enjoy.
Yeah. Okay. So basically, these operons have three main mechanics, which is just the promoter, the promoter, the activator, and then the repressor. And both the promoter and the activator are bind together, because like the promoter could like replicate, like the promoter is basically RNA polymers, and basically the DNA where polymo is okay. Let's see, open activity, central mechanics, blah blah blah. I'm just reading my notes right now. Okay. So the first thing that binds is the promoter, because like the promoter transcribes the codons for the genes, and basically, you know, all the tRNAs like just like builds one amino acid at a time, and then like as they keep like reading the genes, the tRNA comes in and they start replicating, not replicating, they just keep adding on amino acids on top of each other until they get like an like amino acid. Yeah. And then let's see. Polymers. Okay. The second thing that it's also part of like of use of operons is the repressor, which like stops the the action of, it's all in prokaryotes. So basically prokaryotes can produce protein, but like the repressor stops the prokaryote from prokaryote, no, the repressor stops the operon from making more protein, and then like so there is no transcription. Oh yeah, and transcription is like reading the DNA, and then because like transcription has a C in it, so it goes first, and then translation is translation goes after transcription, and translation just like involves just putting the like okay involves putting all the translated DNA, you know, because like they need to like have DNA needs to transcribe itself into mRNA, like to get all the protein, and then like when it goes into the protein, it becomes into the ribosome. When mRNA goes into the ribosome, it turns into protein, but like that's eukaryotes. But and we're talking about prokaryotes because they have a separate function. So, and also, yeah, activator, and promoter bind together, and activator speeds up the process right here. Okay, yeah, right here. Yep. And basically, it binds to the target DNA of, oh yeah, the DNA of the, since like prokaryotes have like, are unicellular, or like, wait, no, they have circular DNA because it's just one whole loop. And unicellular would be like viruses, which is just a single strand of DNA. So yeah. All right, we're getting there.
Yeah, I like how you personify each concept as well. Is like this guy is telling this guy to get up and get ready. Hey, we're about to do something, and then it helps like stick like the concepts more. That's good.
It
That's
also
good.
helps if someone's actually listening, because like I wouldn't do this on my own. I need, or like maybe I could just like pull up one of your YouTube videos and just like
like one of the YouTube videos where we were studying together or like talking or something like that.
yeah, maybe.
Right.
That sounds on the doc. I'm not gonna review their information, but like
Oh,
yeah.
shoot. Yeah. But when is your exam for this?
Tomorrow,
Tomorrow.
second period.
Uh-huh.
It's like at 10.
Shoot. Okay.
I go to school around well, I wake up at 7. Well, I have like a really decent schedule. I like sleep around 7:30, 11, and I wake up at 7, which is 8 hours.
Yeah, that's good. That's good. So then you have some time in the morning to like review a little bit before your exam. You got this, Ryan.
Yeah. And
Yeah.
basically this is like the green thing is the activator, but like these things, I forgot what this structure was called. Wait, does it see? Okay. So the my teacher just said that this is the key, like
Oh.
to like, you know, the car that like
Uh-huh.
drives everything, because like, you know, this is like, because like this speeds up the process, and this is like the one that's doing the process. So yeah, and without this, without the key, the car can't move, you know.
Oh, yeah. I like the analogy. Makes
Yeah.
sense. Are these your teacher's notes?
Yeah, you know, my okay, one little thing, she like my teacher's voice was like all hoarse like the whole time she was teaching, and like we didn't understand a single thing.
Shoot.
Yeah.
What the heck? Is it usually horse, or was you just sick that day?
No, it was like a bad day. Like she was like gone on like no, she was here on Monday, Tuesday, and she always had like she had a sore throat. And then like on
Oh,
Wednesday today, she's absent.
oh my
So
God. What the heck?
yeah, and then my Spanish teacher was also absent. So I had like two teachers missing.
So you had like TAs. Oh, I mean not TAs. You had
Just like regular substitute teachers, but yeah.
substitute teachers. Yeah.
All right. So since we like, oh yeah, let's see the genes. So basically, the repressor stops the promoter. Is the one doing the DNA synthesis, which is the RNA polymers, because it's just reading, reading. It's reading and also synthesizing at the same time because it and like fun fact, the RNA polymers synthesizes at like 5 prime to 3 prime and then but reads 3 prime to 5 prime.
Oh yeah, I
So
always get that mixed up. Like it
yeah.
synthesizes 5 prime to 3 prime and reads 3 prime to 5 prime. Is that what you said? I'm not sure.
Yeah.
I forgot.
Yeah, you said it right.
Okay. I remember those tests, the questions, like it shows up over and over and over, like for different bio classes.
True. Let's see. No.
Do you also ask ChatGPT to create practice forms for you to practice?
I say, well, okay. So I asked ChatGPT to like ask 30 true and false statements about operons and with explanations. And literally, I listed every single question that I had about it. Like, where does this come from? Everything, and then just like spamming,
Yeah.
So let's see. Let's. What time is it? Okay, we still have time. Because you're just gonna go to sleep. So
Yeah.
inductible. Wait, I have the notes on my phone because like my teacher was just writing a whole lot of notes and then like just takes them off the screen for 1 second, just like, oh, they're gone now.
Inducible.
Wait, I have the notes. Is this it? No, it's wait. Wait. Found it. Okay, so inducible is turning on or like induces, which is just like causes basically. Induces transcription and uses an inducer. I think the inducer, wait, no, that is this because I mean that's like my prediction probably. Like because like this is the activator already. So like if this is like the one that like turns it on, wait, no, this is just the helper. This is the key, but that's not the inducer. I'm like figuring things out. Wait. Also, I forgot what this thing was. Wait.
I think the inducible and repressible operons are different operons and how they operate, like how they work.
I mean, on my notes it says turning like inducible means turning operand on or induce transcription uses an inducer, and then like the repressible is the turning an operand off by repressor or compressor. So yeah, so repressible just represses, and inducible like induces, which means causes. So those are the two types, and I guess what they're meaning is like that's either like activator. Okay, I'll just do more. I'll like search a bunch of things on ChatGPT, but like I really need the good grade on this thing. Okay, TRP. So basically, I don't know what. Wait. Okay, so tryptophan. Basically, TRP is the enzyme that makes tryptophan. Actually, it's basically. Like you can see that like TRP is right here, and like when you search like like the amino acid chart, and then like you see like the like guanine, cytosine, adenine, and thymine, you can like, and then like when you like when those like these combinations of like genes are paired, you can like see like the result they have, like, and like there's 21, I think there are 21 wait 21 amino acids. Yeah, there are 21 in total, I think. So brain fart. Let's see. RNA polymer spines operator. Oh wait, so that's operator, that's promoter, that's promoter. Wait, I've only been talking about promoter. and an activator. Wait, and then there's operator, and then wait. Let's see. My notes don't say anything about the operator.
Oh shoot.
Wait. Okay, where repressor binds. Okay, there it is. So the promoter is basically just the promoter, and it's basically just the go and stop pedal then, because like the operator would be like the entire car, the activator would be like the key to the car, because you could just put a car in neutral, but like promoter would be just like the promoter would just be like the neutral, like just put your car in neutral and it'll just go forward, but like really slowly. The activator would be like the key, and then the operator would be like the repressor, basically. Or like, yeah, because like I don't know, I don't have a lot to go off of here, like promoter and then operator. I think that's what my teacher was trying to say. Yeah.
Promoter and an operator, right? Do you also I don't know if you have typed out notes or anything, but you could download it and import it to ChatGPT, and ChatGPT can read through that document and then tell it to give you a study guide or create a
These are all
test
images, so I don't know
based
how they
on
would
that.
read images, you know?
Oh yeah, yeah,
So like also like I kind of see a mistake in like where like my teacher went wrong, because basically these two things like bind together, but like DNA receptor and then activator binds here and then here, and then where it binds. Oh, okay. I see. I'll search what operator, like more about the operator, but yeah.
yeah,
Yeah, I'm finding the holes.
yeah. That's good. That's good.
Okay, so TRP makes tryptophan, and like if there's like a large amount of tryptophan in your system, your brake, your repressor would block. Okay, so this is the tryptophan. This is the enzyme, actually amino acid. This is a protein, right? Yeah, because it comes from TRP, which is from the amino acid, like it's guanine, cyanidine, adenine, thymine, and like yeah. So
Yeah.
basically, yeah, and then like basically just binds to the repressor, and then it just stops like the polymers from like ever reading or like transcribing anything. And then if there's like a low amount of tryptophan, um the body like needs like no the not the body, this is eukaryote, so like the not eukaryote, prokaryote. The prokaryote needs that like protein, that certain amount, that certain protein, so it's going to bind to the promoter, and just probably with the activator too. Let's see. Let's trying to find my notes. Yeah. All right. That's pretty self-explanatory. Brake is off, and like if there's low tryptophan, nothing binds to this little gap right here. All right, and it just goes. But there is no activator, so it can like go with like it can just move slowly without its activator. So that's yeah. Okay, we're reaching like the middle part. So this is the lac app. the operon, and
Mhm.
basically I don't know the difference between LAC-Z, LAC-Y, but they're all enzymes that break down milk or lactose. And these enzymes are called lactase. So the operon has a cap site. That's like the main thing, because like, you know, the cap the cap binds to the camp site. She forgot to put camp, but like you can see right here that there's like a gray rectangle on top of the cap site.
Yeah.
And
Cap.
basically what you can like just imagine like seeing camp on like
Camp.
CAMP, and
Yeah.
basically these two things are basically the activator on this thing, because like, you know, like she color coded it, which is really nice.
Yeah.
And like attention to detail, but like you can
Mhm.
see that these two things are the same, and these two things are the same.
Yeah. Right, right,
Mhm.
right. Dang, same color too. That's good.
Yeah, no confusion.
Yeah.
So basically the cap site binds to, I hope it's like, no, the promoter, like, you know, DNA replication, not DNA replication, I'm talking about the synthesis of like where operons start. They start at the beginning of like the transcription thing, and like the cap site is just an add-on, but like the real thing, like, you know, the AUG, the start codon, like is right here, not right here. So yeah, and then we got our repressor and then our promoter right here. So in the promoter, you know, this lands on the start codon. So like any type of replication synthesis, like making of any protein starts like where like the RNA polymers would land, because the RNA polymers is responsible for making the the mRNA to go to the ribosome and then to make protein, because there's a whole process. So yeah, yeah, okay. So when there's no lactose, our body makes like our natural source of energy comes from glucose, and like our second natural source of energy comes from milk, which is why babies drink milk like sometimes, and they don't really have the capacity to eat like whole foods. So that's where it comes from. This enzyme that breaks down the milk, like for our bodies, like also helps with like the digestion, because, you know, our cells, the whole reason why we need this enzyme or like protein to like digest milk is because our cells can like digest like the milk itself, like the lactose, like, oh yeah, the lactose is like can't absorb into our cells, so like this enzyme needs to be pumped out to like break down it into like to go into our cells. So without lactose, with any lactose, and like, you know, you can see the repressor. So that means that, you know, that no milk enzymes are being formed. So that means that our main source of energy would be glucose. And right here you can see when lactose is absent, the lac repressor binds tightly to the operator. Oh, and gets okay, and it gets in the RNA polymerase way, preventing the transcription. And then right here I wrote, oh wait, is it right here? Okay. Oh, this is much better. I could just say it right here. Okay. So you could see that the cap, you know, there is like only cap and no camp. So like there is like there's no key to like the cap, because like, and like there's nothing, so you can't like, it's gonna go really slowly, and this polymers is just gonna be in neutral the whole way. But since there's a repressor, the brake is just blocking it, we can know that like there's no milk enzyme being formed. So that means our, you know, and there's glucose present and there's lactose absent. So there's glucose, there's a plus right here, just imagine it. There's a lactose, there's no lactose at all, so there's none, so it would be minus. There's a cap that binds. You can see that the cap is all the way over here, so there's no binding. there's no key. And then the repressor binds, which is, yes, you can see it right here. It's all of the questions like right here is gonna be really easy too. And the level of transcription, well, let's see, cap, there's glucose. So basically, and like this is the cap site, blah, 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 and then there's no
Upregulated, downregulated. I don't know.
I'm like reading my notes. It says that there's no transcription.
No
But I think
transcription.
yeah, there's no transcription because like
The repressor is in the
for
way.
the milk enzyme, not like glucose. Glucose has its own cycle.
Right.
Yeah.
Mm-hmm.
This is like for us, I think.
Mm-hmm.
Because like I'm not sure if like this would go to like humans, but let's see.
Yeah.
Glucose is present but lactose is absent. So basically we can see that the cap is like not attached to the site, and then the RNA polymers has no like repressor, so it's free to go. And since there's like glucose present but lactose absent,
Oh, in this case, this lactose is present, right? I think lactose is present.
no, lactose is absent. Wait, no, present. I'm yeah, sleeping is important.
Yes, sleep deprived.
No, I don't know. Okay, so basically we can see that both glucose is present since it says right here. Lactose is also present since like since the repressor, like there's no like indicator, but we know that lactose is here because the RNA polymers has like permission to go. Yeah.
Right.
So that's plus. That's also another plus for lactose. And then cap binds, there's no cap. Repressor binds, there's no, the repressor is all the way over here. The level of transcription would be low because basically your car, the RNA polymers is in neutral, and the cap is the key to the car to start the car. But like since like just gonna be a really slow process, like to like build that energy, like build that protein for the cell. And then our glucose, okay, number 3, glucose is absent and lactose is also absent. So basically we can see that there's literally nothing being produced because this is like worst case scenario. You have no food and you have no milk, and basically there's nothing being produced. Even with like the key, this is basically when you have like no fuel in the car and like there's nothing.
Everything stopped.
Yeah, we can see that like the repressor's on, and like the cap, which is like basically the little camp that binds to the cap, is the cap like tells the camp tells the cell, the cap, I mean the camp tells the cap to like, hey, we're starving, we need to make this protein faster. And then basically if like the activator, both of these things bind to the site, but there's no food, so basically, and like there's nothing to like eat. And then basically this is just like both these things are present, the cap binder and then the repressor binder also is like blocking the flow, and then there's like no food at all. So this is just like no transcription whatsoever. And then our last one is glucose absent and lactose present, which is like when you just drink milk the whole day and then you don't eat any food. So basically your cap and camp like get like a boost where they have like the energy, like, hey, there's like a lot of milk to synthesize, because like ours, like if it's like diabetes where like your cells can't absorb like the insulin, not insulin, your cells can't absorb the sugar. And like if it's like if it absorbs into the cells, it's a bad thing. For this thing, it's the activator. If lactose can't like be absorbed into the cell, it's basically like it makes you lactose intolerant, which means like you get allergic to milk. So this camp thing is important, since like if you drink like a lot of milk but there's no glucose, um basically it's just telling the cell to like, hey, like they need to like start breaking down milk as fast as possible, or else it's just they're gonna have an allergic reaction to it. And then our repressor is like out of the way to like allow RNA polymers to start making the enzymes that break the proteins that break down milk. And
Wow. Nice.
need sleep.
That's good. Yeah. Oh. Yeah. Like, how long were you up today?
So long. I mean, I've literally like, okay, so like last week, I was like, okay, story time. It's gonna take like 10 to 5 minutes, 5 minutes almost. So actually, it's gonna take a lot shorter. So basically, like on Saturday, I was like up at like 6 in the morning, and like I'm doing jack shit, and basically it was just really bad because like I was like, oh, what am I doing with my life? And then I just slept 16 hours, and then like after that, I was like, it was kind of like the like the transformation I had like 11 months ago, where it's like I cut off everything. Like this time, it's just like I was like at baseline where I was just okay, it's time to like start building new habits because I'm like I have like all the socials are gone, all the video games are gone. It's like okay, time to focus on sleep. And then like I slept the whole weekend, and then on Monday I like basically got like 9 hours of sleep because I went to sleep at 10 o'clock. And like I said, like I don't know if you can like read my arm. Let's see. But basically, I just write a bunch of things on my arm just to wait.
Oh yeah.
Yeah.
I
Okay.
see.
Yeah, you can see the writing, but basically, I just like like I need to be more positive. All this negativity won't like help me at all. So
Yeah.
basically, just like now it's the habit, and also like sleeping 9 hours is like the goal nowadays. Where like I can do all this work, but I need to hit the save button in my head to save everything.
Yes. Process everything, because you're running without sleep, you're gonna blink out during the test and like forget everything that you studied for. So hit that save button.
Mhm.
For sure.
Yeah,
It's
but
good.
like it. Yeah, it's really good, honestly. Just like having like 5 things, like I wrote 5 things I'm grateful for on my arm, like, and then there's like a box of priorities, 3 priorities I have: eat well, sleep well, drink water, and then like a schedule on my wrist. So just like
Yeah.
like 11, 10:30 sleep,
Uh-huh.
and then yeah, and then the yeah the I promise myself from now on I'll get 9 hours of sleep, and and then like eat well, sleep well, and drink water because like I've been ignoring drinking water because like I just like what I don't drink water until like I come home at like 6 o'clock. It's like bad because I only drink water one time out of the whole day, and then I sleep like 4 hours. Used to
Oh my
used to
gosh.
like 4 or 5 hours, and then like it was bad because I did not like take care of myself. Eat
Yeah.
well because I would only eat one meal a day. Yeah, and then
Oh
like
my God.
and now like I'm eating 3 meals a day.
That's
I'm like
good.
sleeping 9 hours, and I'd like bring a water bottle to school if I'm thirsty.
Prioritizing health, health as
Yeah, and
well.
then like I realized, um, oh yeah, just like if I ever scroll on social media, which I did today, like at 1 hour, because like the like, hey, you've been on this app for a long time, and then please consider closing this app. And then I just did it, and then I just started studying. It's like, and then I caught up, and then I'm back. I'm back.
Yeah.
Yeah.
Dang, that's good. That's good.
So whatever like time I lose on like screens, I'll like subtract it from my sleep, and then I'll say never again, or like maybe just like this really helps because like whenever I say it's like, oh, I just like count from 1, 2, 3, 4, 5, 4, 3, 2, 1, and 0, and then it's just like gets me back on track.
Yeah. That's good. That's good.
Yeah.
Using all those tips that you learned, and then it's been helping you making progress too. So good. And the Sunday night when we have the offices, we could talk more, catch up more, and then I could let you know all about my stories on how I studied for these exams these last 2 weeks, because it's been crazy. Last week and this week has been back to back to back to back exams, and now I'm finally over over it.
Good job, honestly.
Yeah.
It's just like I've been managing sleep really well, only like Monday, Tuesday, and today. Yeah, just like around 8, well, yeah, 8 to 9 hours.
That's good.
Yeah. And like I can't like take it for granted like I did today. It was like I just like didn't do anything. I just scrolled for an hour. It's like, oh no, I need to be like I need to like consciously remind myself why I did this in the first place. So
Right. That's why you wrote it on yourself.
yeah,
That's
just
good.
write it.
Yeah.
Yeah, just like having set things in place helps. Just like going to home, not starting on homework yet, but like basically wash your face and then do a Duolingo session, which is unrelated, but like gets you in like the mood to
Oh, what
like.
language are you learning in Duolingo?
Oh, I'm learning 5.
Oh, 5 languages?
Yeah, but like I'm only using Duolingo for Korean, and then like I'm English, Spanish. Spanish. I'm in Spanish class, so like
Uh-huh.
um German, and
Uh-huh.
then Cambodian, my home language.
Oh, wow. Well, what inspired you to learn German and Korean?
Like on okay, German's the earliest one, but Korean was like around 10 months ago where I was just like, huh, I think I should download this app because like I never heard of Duolingo before. And it's like, Duolingo, what's that? And then I just downloaded it. It's like, oh, that's really cool. And then I just do a lesson a day.
Oh, yeah, that's good. That's good.
I mean, I haven't been consistent, but I've been consistent really well, like in the past like week. So
Yeah.
yeah. And then German's like the like most confusing one, I think. Just because like I don't have the time. I like look at the Discord because my friends made a Discord for it's like, hey Ryan, you want to learn German? It's like, yeah. And then I look at the Discord sometimes. I like memorize some phrases and then I say it back to them when I see them.
That's good.
And then Cambodian, English, and Spanish.
Mhm.
I'm like surprised like how much time I have as like because like if I just like 23 hours doesn't make isn't like as big as like 24 hours. Like if you just subtract 1 hour of your day to like take care of yourself, then like basically it'll give you like you have more energy to do stuff. You like have more time to like there's no like you're not thinking about other things when you're like doing the task. And then like there's like number 3 is just like it takes like a load off your shoulders where you don't really feel like you need to procrastinate or like you feel like you should do other things while doing the work.
Yeah, and as long as you get in the flow, the zone, you want to keep
The
the
zone.
momentum going. You don't want to stop the momentum because when you stop the momentum, it's gonna like have frictions to start again.
Oh, for momentum, like like my like I kind of realized like I was watching something that's just like oh that really makes a lot of sense and like just like a lot of habit stuff, but like basically, I just like how like I would describe my past habits would be like a slingshot method, like a slingshot
Oh
method.
yeah.
Like I'd pull myself back, like I'd literally just like do something really like just like do something like just bad for myself and health in general, and then I just use that pain to like launch me forward, and then
Forward, yeah.
yeah,
That's
and
good.
then like and then basically it's just like oh I'm gonna use all this thing to propel myself, but then like you kind of realize that like you just stop, like you
Right.
just
That could be fuel to your
and,
fire.
like,
Like
it's addictive too, cause like, once like, you just, like you go, and then you stop, and then you have to, like, pull yourself back again, and then you have to go, and then, like, it's just a never-ending cycle where, like, you can't really like, like, improve one day, and then you make this mistake, and then you just stay the same. You plateau, basically. You're just
right.
plateauing multiple times, and then and then
Yeah.
I realized that like for me to have a stop button, I need like the good things like sleep, like eating, and then water, and then exercise, and like all the things that I thought were like unnecessary, like to like do school, because like I was like, oh, I just focus on school, and then like whatever time I have left to sleep, I'll sleep. But like I wouldn't like schedule like sleeping. I would just like go to sleep when I'm like already like hella tired, and then
All right. I
or
know, like
just dead tired, or
nothing
like
left in the tank.
basically just like I sleep with the light on. If like oh I'll just come back an hour later, and then I like just just sleep with the light on, just like on my bed, and just like I don't have the energy to turn that light off or my computer.
Yeah, I remember. You told me that your mom was like mad or something. Your mom told you to not do that again.
I'm wasting energy.
Yeah.
And then like only recently I just like turn off all screens or computers by 11. Which is good because like I thought like I wouldn't have like a lot of time, but like I do have a lot of time. It's just like I need to like do like the things I've been doing right now, like same routine basically.
Right.
I just need to have a consistent morning routine where like I'd wake up at the same time and I wouldn't ignore my alarm.
Yeah. Consistency and time management is key for this. Right. Dang.
Yeah, so tell me more about it, like the whole week, like as an experience, because like it's only been experiencing it for 3 days, but like I'm starting to like a little like fall off a little bit, but like I'm just gonna delete Instagram right now off my phone.
Oh shoot. Okay. Dang.
Oh, it's already deleted. It's already deleted. Never mind.
Yeah. I'll let you know more stories about it on Sunday. But right now it was nice catching up with you, Ryan. I'm glad that you updated me with these stories.
It really is good. Like I'm finally winning, and like I don't like I'm not like I'm not like pulling like myself by a slingshot anymore.
Yeah, that's good. That's good. Yeah. Let's see. Are you gonna make it to so Sunday's hangout session, Ryan? So we could like
Yeah, I
chat
can.
more?
I'm
Yeah.
not really
That's good.
doing
That's good.
anything, but
9 to
yeah.
11 p.m. It's just us talking.
Mhm.
Yeah. Okay. Yeah. I'm gonna go get ready to go sleep now. But it was nice talking to you, Ryan. Yeah. Good night.
Yeah, that's perfect. Thank you. Bye. See you
Bye.
on Sunday. See you Sunday.
Yeah. See ya.
Thank you.
Good luck on your exam tomorrow.
Oh yeah, thank you. I need the brain. I need my
Yes.
brain.
Okay. Bye.
See you. Bye.
Bye.